Welcome, everyone. Thank you for joining today's webinar. I'm here with Pavel Avgustinov. Pavel is the VP of Engineering for QL, Semmle's query language that performs code analysis to find critical variants of vulnerabilities. In today's webinar, Pavel will demonstrate how Man-Yu Mo, a security researcher at Semmle, was able to find a number of CVEs in Ghostscript in November last year. We'll leave plenty of questions, time for questions at the end. To ask questions, you can type them in the chat window as we go, and we'll answer them at the end. This webinar will also be recorded and available online soon after. Over to you, Pavel.
Thank you very much, Sumitra. Welcome, thank you for joining me today. Word of warning, all of this is going to be live demos, so I expect things will go wrong repeatedly. Please bear with me as that happens. So let's start by briefly setting the scene for what we're trying to do here. We're going to be looking at Ghostscript, which is the leading PDF and PostScript interpreter around the world. So it's a piece of software that converts between PDF and PostScript and TextPS and many other formats, producing various other formats. And so it's actually something that's used behind the scenes by many document viewers and other utilities. So the impact, if anything, we find might be quite significant. Ghostscript itself is written in C, and it includes a set of C procedures which are provided as primitives to the PostScript files. Now, a word on the history of Ghostscript itself. It's been around for quite a long time. It was first published back in the 80s. And of course, back then, the notion of a network-based security attacker was quite unheard of. The World Wide Web only came into existence in the 90s. And so the security model, or the threat model, was very different back in the day. Ghostscript has been subject to a number of security audits from Project Zero and from various others. In particular, Tavis Ormandy has found numerous bugs, including code executions within Ghostscript. And recently, my colleague, Man-Yu Mo, also found a number of variants, and that kind of variant is what I want to talk to you about today. So we're going to be focusing on a class of vulnerability known as a type confusion. A type confusion arises in a language like C when a particular object is interpreted in a way that is different from its type. So maybe you have a struct, but you treat the pointer to it as if it were a simple car pointer, and so reading or writing to that will mess up the internal state of the struct and lead to various interesting consequences. The rest of the talk will be largely in the form of a live demo. So the first thing I want to highlight is that Ghostscript is in fact a full-fledged programming language. We think of it, or at least I thought of it, as a format for fixed documents. However, behind the scenes, it's actually a language that happens to have good primitives for drawing things on a device. And so I can actually do things like write a classical Hello World program. And Ghostscript itself is what's known as a stack language. So things are usually given to it in reverse Polish notation. So if I type 2, 4, add, for example, this will add the numbers 2 and 4 and put the result on the stack. If I then type 7 mul equals, this will actually give us our answer. And so this is where the ideas for the kind of exploits that we're going to be hunting come from. A PostScript file is just a script in this language. And so if it can confuse the Ghostscript interpreter into doing the wrong thing, that's a problem. So we're also going to have to talk a little bit about what's present in the Ghostscript codebase, or how things are represented. So what I have here is QL for Eclipse, our IDE for QL. And I'm going to be looking at an old version of Ghostscript, namely from October last year. Just to be clear, the vulnerabilities we're going to be looking at have in fact all been fixed. In the Ghostscript interpreter, the values with which the language deals are all represented as a particular type. And a quick look at the code is going to tell you that it's a type called ref. So we can write a quick query in order to find out what exactly that type is. So from type T, where T dot has name ref, select T. So that's how we will find all types that are called ref. We'll see that in this instance there are two results, and there are two distinct type defs, but they do the same thing. They type def the struct ref_s type to be called ref. So actually, we really should be looking at what that struct is. So quickly tweak the query to do that. And here it is. So it's a struct, and this is the representation in the Ghostscript interpreter of Ghostscript values. We see that it has two fields. The first field is one of these type attribute structs, and the second is a big union called value. This is because Ghostscript itself, it has many built-in types, and they all can be represented in this ref_s struct. Depending on what the type says the value should be, you're allowed to read either the int value or the bool value or the real value, or you're allowed to interpret it as a as a file or a procedure or a struct. But of course, if you end up reading or writing the wrong field of this union, then that's exactly the kind of type confusion vulnerability that we want to find here. So let's start by defining a few helper predicates to model all of this. So I'm going to start writing some KL utilities here. First, we're going to be interested in reads of those union fields, which are stored in the ref. So in Surface C, they might look like ref value.int val. That would read the ref as a integer. So I'm going to define a predicate called union access, and it'll relate an expression with the value which is being read as a particular type. And so here we're going to basically just say it has this form. There is a field access in the middle, which has which is declared in the ref_s type, and it's qualified by the ref object, and the field that's being accessed has the name value. That's the union, remember. And finally, the typed value which we're reading from that union is the qualifier of the value. So far so good. It's a fairly direct expression of what we said up here. Let's quickly inspect the results that this predicate, I need a placeholder query in order to make this happy. Let's inspect the results that this predicate is going to give us when we run it. So as an example, here is an expression whose type is ref_s, and here is the typed value that we're accessing there. So we're reading the union, and then we're accessing it as a file. Okay, so we can see there are quite a few results, 2.7 thousand. That's unsurprising. After all, Ghostscript deals with these values a lot. You'll also see that the code base is very macro heavy. So this make bool thing that looks like a function call is in fact a macro that will take the ref op, and it will make it a Boolean value by assigning to its type, and then it will give it the value that it's given there. So behind the scenes, there is macro expansion going on, but with the query that we're writing, we don't need to worry about that too much. Okay, so far so good. Let's also write a helper that allows us to reason about type accesses. So if I go back to the the ref structure, the field that tells us about the type is one of these tas things, which is defined up here. And type utters is how the interpreter will represent that the value has a particular type. So if you want to read a ref and say, take its bytes out, you first should check whether type utters indicates it's legal to read the bytes. All right. So we have a helper that tells us when we're reading a typed value. We also want a helper that tells us when we are accessing the type address. So for example, that would look like ref tas.type address, like this. So as you can imagine, it's going to be very similar to what I wrote above. Type access on a ref. And in fact, it's going to be so similar, I'm going to largely copy what I wrote and then edit it a little. So I don't need this bit. And the intermediate field is now called tas, rather than value. And I guess I'll also say that type address. So the type address field has the name type address. So we're saying this because above, when we're talking about the union, we didn't actually care which field of the union we access in order to read the typed value. Any field of the union is potentially interesting. But down here, only one of the fields in the task struct is type access. So as before, we can quickly sanity check that we have something meaningful by executing this. Okay, so 2.9 thousand accesses, and here is an example where, again, in a macro like make real, this will assign to the type address field in order to indicate it's a real value, meaning a float, and then it will give it that value. So at this point, we can actually write a first attempt at our query. We can look for accesses to a typed value which are not accompanied by a type check. So we're going to use a variable, which is the ref that's being accessed here. And read is going to be the typed field. So it's a union access on ref. And moreover, it's not the case that there is a type access on ref. Yes, of course, I need to say that we are looking for accesses to that variable rather than the variable itself. So this query now very simply says we're looking for union accesses of a variable where there isn't an accompanying type access. I'm going to quickly run it, see what happens. The other thing that I think we'll have to refine this to is that, well, let's have a look at the results first, actually. So here is a ref. This is the field that's going to be accessed. Here is a read that is not accompanied by a type access. So we're looking at ref array packing.value.boolval. We're treating it as a bool. And ref array packing, well, it came from somewhere. This is the main interpreter loop, actually. So it's actually quite hard to make sense of the control flow that, that is going on here. But if I scroll down, let's have a look at another few examples. Here is a ref which is accessed as a pict without checking that the type is appropriate. Now, most of the time when this happens, this is actually because the code knows about some invariant that establishes the type is correct. So this function, for example, it will read the bytes field of op, but it's only meant to be called on arrays. So the caller should have checked whether it has the right type. Now, in order to focus this a little bit, we want to zoom in on instances that are easier to control as an attacker. So if I can supply a PostScript document, I want to find cases where I can reach one of these typed reads without a type check. And this is where this pattern is very interesting. So in Ghostscript, functions which take an iContext T pointer are pretty much routines that are invoked by the interpreter. And the context is the global interpreter state. We read the top of the operand stack using this macro called OSP, and then we use that. Now, the reason this is interesting is that the operand stack is directly controllable by us. Whenever I type a value into PostScript, it ends up on the top of the operand stack. So what I'm going to do is start reasoning about values that came from the operand stack. So you can see here, for example, op is going to be used down here to allocate an array. So in this case, it's actually being made into a particular type. But in general, if this was used without a type check, we would have a vulnerability. We need to understand just very briefly what the context looks like in order to express an access to the operand stack. Okay, I must have mistyped something there. iContext T is the type. So we're looking for a type of this name. And as before, we actually find it's a type def to this Ghostscript context state type, which actually tells us what we need to model in our query. Here's the definition. It's a big old struct that contains interpreter options and various functions and settings. And crucially, down here at the bottom are the three stacks that are available to Ghostscript programs. One is the dict stack, which is effectively a set of scopes. One is the execution stack. So when you call a procedure, it goes onto that. And the operand stack is the one that I'm most interested in. So I'm going to define a very similar predicate to what I had before that captures a pattern like this. When we read the context pointer, take, for example, the op stack and read its stack field and get P, which happens to be what the top of the stack is called within that data structure. So actually, let's mix things up a bit. I'm going to make this predicate return the value rather than take this as an argument. So it returns the field access to P. Field access, stack top access. And again, we'll have the context. And we'll have, let's also have the kind of the stack. Remember, there are three stacks, the dict stack, the execution stack, and the op stack. So we may want to reason about each of them. And so we can do that all at once. So as above, I'm going to need variables to do these intermediate steps. I need to step to op stack, and then I need to step to the stack field. And from there, I'll get the top of the stack access. So stack. So, and this is going to be, again, quite similar. The qualifier of the stack field is the context, and the target of that access, so the field that we're accessing has the name. In fact, what I'm going to do is something weird here. So it has the name kind plus underscore stack. So this will allow us to see later which of the stack fields we're reasoning about. Then on that, we get a qualifier, which is the stack field. And then that has the name stack. And finally, the expression we're actually interested in, the result, which is the field access to P, is qualified by row stack, and it has the name, its target has the name P. Okay, let's sanity check by quickly executing this predicate and confirming that it will behave as we expect. So here is an access to the context pointer. It's hidden behind this macro, but actually we don't need to worry about that because we have the query can range over the expanded code. And of course, in this case, the access to P is also behind the macro, but at least we know it's working. Okay. Now, we're going to want to reason about where that value flows to. Remember, the results that we had before just said there is a typed read without a type check, but I want to restrict those so that only results are reported if they came from a stack. So I'm going to import an additional library to help me with this. So the taint tracking library in the default distribution encapsulates utilities for reasoning about how data propagates in the program. And in particular, it will allow us to reason about how things flow. Let's have another hello predicate as well, which is going to tell me, given a stack top expression, which is one of these accesses to P, what it might reach. And so stack top is going to be a stack top access. I don't actually care which context it comes from, but for now, let's say we're interested in the op kind of stack, so the operand stack. And this is where we're going to use the data flow library. We're going to say there is local flow between two things. The first thing is stack top, and the second thing is the result, the thing that we're returning. So let's quickly evaluate that again. It's always helpful to look at the building blocks that we're creating and keep an intuition for what they are going to do. Okay, so here is a stack top, and here is a value that it flows to. That's itself. Well, yes, of course, the value flows to itself. But the more interesting one is this. The value also flows there. And it also flows here. Now, you'll see the location is a little bit weird. That's because check read type is a macro that has expanded to several uses of op, which are all reported. And then it also flows to there. Okay, so this utility predicate actually now gives us a way of restricting our results to things that come from the operand stack. So rather than talking about the variable, let's say that we have the stack top expression here. And then the union access flows from stack top. And it is not the case that there is a type access which flows from stack top. I'm going to select stack top here. So a relatively small change in text, but it should significantly help us focus the results. Let's evaluate the whole thing. So you can see we've reduced the number of results from several hundred to 25. And if we look at a few examples, here is an access to the stack top. And here is a read of it as a struct, which is unchecked. So our pointer here is indeed a macro that will read it as a struct. And we can see there is actually an invariant documented in the comment that says the top of the stack is meant to be a struct. So it's not checked locally, it's checked hopefully the callers. So there's a question in the chat about a little bit more detail on the purpose of the data flow package and library, which is used in flow from stack. So it's all about propagating, or rather tracking how values propagate from a particular source to other places in the library. So the good intuition is what we looked at before here. This value within this macro comes from the top of the stack, and it propagates to all of these different things. There is data flow between that reads from the top of the stack and these other expressions in the program. At the moment, we're only using local flow, which will track data flow within a particular single function. But the library also allows us to reason about flow of data between functions. And we'll actually take a look at that as we go on. So, where are we? We have now refined the query to tell us about locally unguarded things which are potentially risky, and we can audit them. These results are kind of interesting. Actually, this is a result that perhaps it's worth ruling out. So what happens here is that make real actually assigns into the pointer rather than reading from it, and so that arguably there's not going to be any type of confusion from that. Yes, why not? Let's refine the query to remove that. So we want to ignore cases where the read is actually being assigned. Well, so it's not a read, I suppose, in that situation. Rather, not read is any assignment a dot get L value. So it says exactly the same as before, but it will hopefully remove some of the results which are less interesting from a security perspective. So 21 results at this point, and a quick audit of them. This is the one that we looked at before. Here there is a non-local invariant that the type has to be correct, and if it isn't, it's type confused. Here is another example where this function just assumes the top of the stack is going. The top of the stack is going to be a struct. It's actually used here as part of a fairly complicated handling of some data. In fact, a lot of these CIE def finish, CIE def G finish, and CIE ABC finish, they're all very similar. And I think from looking at the caller code that this is actually going to be okay. Looking down a little bit, just sampling some more files. String delete file, this is kind of interesting as well. We are taking data from the stack. We're then calling parse real file name on op, which is our stack pointer. And parse real file name is actually what makes this code safe, because if op is not a string, it will return an error code, which is negative, and then will return here. And that means that down here, it's actually fine to read the bytes union field. So our query hasn't currently said anything about non-local type checks. We've kept it simple. So it's understandable. It reports this result. We could refine it to not do so. And then very similarly, the bottom couple of results here, they treat op as a string. However, they all call this opshow setup function, and I think that's the one that ensures it is in fact a string. So here again, this calls opshow setup, and so I believe all of these results are in fact safe. Okay, well, that's quite common. If we start auditing a new code base, we write a simple query, we check whether it has any results, and typically, if it was as simple as that, a fuzzer would have already triggered a type confusion. So the results that we are left with aren't as compelling. This is where my colleague Manu Mo had a great idea about extending this query in a way that will flag results which are unlikely to have been triggered by a fuzzer. So in Ghostscript, there are also compound data types like arrays and dicts. And of course, if we call a function that treats a stack value as a dict without checking its type, then our query would have flagged that. But what if there is Ghostscript code that reads from a dict, so it takes a value from a dict safely, but then uses that value without checking its type? As before, if the dict came from the operand stack, we can provide it, and that means we can arrange for any type to be contained within it. So we might be able to type confuse the interpreter in that way. So in order to do this, we need to dig a little bit into how the interpreter represents these collection functions. What does it look like in Ghostscript to read from a collection? And I'm actually going to model this as a class in QL just to illustrate another way of creating a reusable library. So there's going to be a class that extends the function class. So function is just any function. Collection fetch function, well, I want to make this class be exactly those functions with which the Ghostscript interpreter will read from an array. The way that I'm going to restrict this is to write something that is similar to a constructor in a normal language, but it will just be a condition on functions. And in fact, as I said, this is something that you have to discover by looking at the code, and I've already done that legwork. There's going to be an input parameter, and there's going to be an output parameter to that function. And there are two interesting cases. This dot has name array get, and in that case, the input parameter is the second one, and the output parameter is the third one, and the fourth one rather. These are zero indexed. I'm just going to quickly evaluate that to show you what I mean. Or, so here is the array get function. It will take an array ref, which is the array, an index, and it will output the value at that index in this array to this pointer. So its input param is the array, and its output param is the pref here. So the equivalent function for dict, actually, there are two of them. I'm going to use a regex match here. It's dict find or it's dict find string. And for those functions, the input parameter is the first one, that's dict, and the output parameter is the third one. Just format that. So if I execute this, we should now see the extra functions that I'm modeling here. So dict find takes a dict and a key and returns a value. And dict find string is very similar, except it takes a dict. It takes the key as a string, but it still returns a value. So we now have this class capturing the functions with which the Ghostscript interpreter will read items from a collection. We can also add member predicates to it to help us use it later. So in particular, one useful predicate is going to be one that tells us what values are read. So predicate reads item will say that from the given collection, we read the given item. And what does that mean? Well, it means that there is a call where the collection fetch function is the target. And moreover, the collection is that argument input, it's the input argument. And the item is the output argument. Okay, as always, I'm going to have a quick look at the contents of this predicate that I've just defined to build confidence that I am doing something meaningful. So 738 results. Collections are quite widely used. So these are for array get. Here is an array get on p names, which produces pref. And if I scroll down to some of the dict functions, here is a dict find on ttcmap, which produces its output in this GID variable. Okay. Now, remember the pattern that I want to find now. We're looking for cases where something came from the stack. It flows into something like an array get. And then later, I'm going to use what came out of the array get. Say, this is probably going to be a pointer, without checking the type of item. That's what I would like to capture. So we're going to need a couple more variables to model the intervening step. So there's going to be a collection read, which will produce an item over here. And from the item, we're going to reach the read. Now, the collection, we said, one has to come from the stack. Collection read is flow from stack top. Now, I need to do this extra step. So I want to get from the collection to an item that's read out of the collection. And to do that, I'm going to use the collection fetch function class that we just defined. So that reads the collection read, which came from the stack, remember, because of what we said above. And it produces item. So it defines the item that we are interested in. And then the union access should be on item. Now, of course, this is not actually exactly right, because item itself will be this argument of gid. But actually, what I want to find is this later use of gid, which uses it as an int. So I'm going to introduce an extra helper to let me do that easily. So data flow node taint from data flow source. So this is a predicate that will say the node we're returning comes from the node that is the source argument. And again, I'm just going to use the library that we imported above, the data flow and taint tracking library. Like this. So now over here, I want to say that rather than directly using item, we track taint from the item. And that's what the union access is on. And similarly, when we say there is no type access to check the type, we want not to flow from the stack anymore. We have this level of indirection now. So we want to track taint from the item. And that would be a valid type check for the item. And of course, we want there to not exist such an item. Okay, so maybe I should have added a few more things to our selection just so we can more easily make sense of it. I'm just going to add all the variables so that we can see what's happening. But even that query already hints at the fact that there are two results we can look at. The stack top is here, so it's in the .set output intent PostScript function, and we reach down here Now, we reach that through, let's actually look at the mover bus thing. So we start here, we read it as a collection here. So we look up n in this dictionary. We define p_n_val, and then we use p_n_val as an int without checking its type. That's exactly what we set out to find. And so if we check the other results as well, it's pretty similar in its nature. So this extra indirection step, I think, is useful to, this is kind of an answer to one of the questions in the chat. I think the indirection step is useful to find places where a fuzzer is less likely to reach. Because in order to get there, we need to have crafted a more complicated data structure. We need to have created a dict which has the right key, which has a value that is an unexpected type. If you're randomly generating inputs, PS files, you're less likely to have hit that case than just, we push a dict and we call a function that treats it as an int or something like that. Now, 2 results is okay, but I was actually hoping for more. And so now we can think about what we need to do in order to generalize this. So the main opportunity, I think, is in this first line. We said here that the collection read directly flows from the stack. And remember, we used the local flow function, which meant that we only look at very local definitions. What if the stack value is passed to another utility function, which passes it to another utility function, which then uses the problematic pattern? So we can use now the global data flow and taint tracking features of the library. Now I'm going to copy a little bit of boilerplate from something I prepared earlier, and I'll explain what it does. So when we reason about local data flow and taint, it's actually feasible to compute all pairs of nodes where one flows to the other, because we're only talking about a single function at a time. As soon as we start talking about global, this becomes intractable for large code bases. And so the library provides this configuration mechanism with which we can tell it what we want to actually track. So we provide a subclass of taint tracking configuration, which indicates what our sources are and what our sinks are. Our sources are just accesses to the stack. That hasn't really changed. And our sinks, well, before we had not constrained that, but now we constrain it to users of the value that we're tracking as a collection that we're reading an item out of. So the thing that I need to change down here, rather than this line, we're going to say any obstack flow dot has flow from stack top to the collection read. All the rest remains unchanged, but now we've leveraged global data flow here. And so if I track it, if I run the query, we should hopefully see more results. There's a question in the chat about why we don't directly use taint from as above. Taint from is actually also local. So if we look at the definition of taint from, it calls taint for a local taint. It will only track taint within the same function. Whereas here we are we're going for the global tracking of the collection. So let's have a look at some of the examples. Here is a call, or rather a stack access. And here is the collection read that we tracked it to. Now this is in subfont params. The stack top is in z-build font, so it's a different function. That wouldn't be captured by the taint from or the local taint predicate that we had above. But then from here, as before, we define p font name, and then we treat it as a string without actually checking what its type is. So you can see that when we use the global taint tracking configuration, it actually becomes a little bit more difficult to see how the taint occurs. We don't really know at this point how we got from z-build font 10 to all the way over here. And we kind of need that information in order to try creating an exploit for this issue. So the final stage of this is to rewrite the query a little bit to use hasFlow path and to select data of a particular shape in order to let our tools expose the data flow path that we tracked. And this is going to be crucial in order to actually try to find an exploit. So in total, we find 23 results. Let's take a look at some of them. So here, we have an array get of subst nwp, which comes from over here in a different function. Now, because we're using the path formulation of the query, we can take a look at the data flow. So we go from this read of the stack to down here. Now we can see subst nwp was assigned something derived from the stack pointer, actually not the stack pointer itself, but something 2 stack slots down. But it's still from the operand stack. It's still fully controlled by the PostScript file. So it flows into this argument to sid fill sid map. And then in here, it becomes the parameter subst nwp. It is passed through to sid2tt car code, or it becomes this parameter, and this is where the array get is. Only at that point do we end up treating it as an array, and we read something out, and we treat that something as an integer, and then we do various other things. That's the kind of type confusion that we're indeed looking for. If you have a moment to read Mo's blog posts, you will find he talks about how to actually craft exploits. And I think the key idea is to leverage these paths that we have. So starting at this stack read, the comment actually tells you how we can trigger this function in PostScript. We need to put 2 things on the stack and call .buildFont0. Okay, then we need to figure out how we're going to make control flow reach here. So that means that all of this sanity checking that happens needs to succeed, otherwise Ghostscript will abort. So that tells us that we need to make sure fmap type is a key in the dict at the top of the stack, and what we put in it has an integer within the right range. And in addition, fdep vector is a key and is mapped to an array, and so on. So we can now pretty much just craft our exploit by putting things on the stack and refining them to get further and further through this function until we hit this call. And then we take a look over here. We see there is additional validation. We need to add font type to the dict and encoding. But if we do that, we'll hit this call. And in here, there is some additional validation. We need to add font matrix to the dict and a rich font. But at that point, we'll be able to reach the type confused place. I think that's roughly all that we have time for in the main part of the demo, but I'll be very happy to take any additional questions that you have. So there's a question about the focus we had on the op stack. So if we look at the sources that we defined, we said that we begin tracking at the operand stack and proceed from there. Could there be type confusions with some of the other stacks, like the dict stack and the execution stack? Well, in a sense, it's quite easy to find out. I could just not say that we want to restrict to the op stack and look at any of the stacks. But in practice, what tends to happen is that the dict stack and the execution stack are much more specialized. So most of what you tend to push onto the dict stack is dicts, as the name suggests. And so, while there might not be, direct type checks when you read from the dict stack, it's probably safe to assume that what you're reading is in fact a dict. Similarly, for the execution stack, most of what's being put on it is procedures. And so using it as a procedure is less obviously wrong. Certainly, as we phrased the query, we didn't get any additional results from removing this restriction. So there might be some, but we would need to generalize something else. There's a question on what the difference is between data flow tracking and taint tracking. They're both provided by the same library, of course. So it all comes down to what exactly it is that we're tracking. When we speak about data flow, we track a particular value. So in particular, for example, the top of the stack through the program. If you do any operation on that value, if you read one of its fields, if you add one to it, if you take its address, that changes the value that we're tracking. So data flow stops at that point. We would no longer report that. Taint tracking is about tracking the property of being tainted. So if we consider the stack top to be tainted, and then later you subtract one from the stack top, that will still give you a tainted value because the original was tainted. And similarly for many other operations that you might do to a value. So which of the two you need rather depends on your particular use case, but in practice, most of the time it ends up being taint tracking. There's another question about the restriction that says there is no type check. So in particular, this might erroneously filter out cases where the type check is erroneously after we've already used a typed value. And it would also filter out cases where the type check checks the wrong type. So you might imagine that we check something as of type array and then use it as a dict. That's true. As phrased, the query focused on the lower-hanging fruit of an entirely missing type check. We could certainly refine this further. So you could imagine that in type access, rather than merely flagging cases where we read the type address field, we could also check which type is being validated here. And then the query could report when you have such a mismatched type check. In practice, I don't think there are any of those in the Ghostscript codebase at the moment, so it wouldn't give us any additional results. For the idea of insisting that the type check happens before the use, again, in practice, we should do that. It's possible, but it doesn't give any additional results because currently all of the type checks are first. There's a final question that I think we'll have time for, which is, do I think there are still more type confusion vulnerabilities like this to be found in Ghostscript? Very likely, yes. With a query like this, you inevitably make assumptions about how to focus the investigation. You're trying to find particular instances of the problem. And here, we very much rely on Mo's idea that there is a collection fetch in the way, which might have hidden the fact that we need to do a type check. There are other situations which might confuse us. So yes, I'm sure we can generalize this or find other variants of the query, which will find issues. Okay, that's everything that we have time for today. Thank you very much for joining me. Thank you very much for your questions. As a quick announcement, the Semmle security team has just published 13 code execution vulnerabilities in U-Boot, a network bootloader used in many embedded devices and IoT things, Kindle and IRM and Chrome OS devices. So if you're interested in that sort of thing, it again uses very similar ideas to what I've been showing you, a similar taint tracking query. You can read more about it on blog.semmle.com. It's the first or second link at the moment. Thank you very much for your time.